Did you know that hydrogen is a chemical element? It has a simple H and atomic number 1. It is the lightest element, and at standard conditions, it is a gas of diatomic molecules with the formula H2. It is colorless, odorless, tasteless, non-toxic, and highly combustible. Hydrogen is the most abundant chemical substance in the universe, constituting roughly 75% of all normal matter. Stars such as the Sun are mainly composed of hydrogen in the plasma state. Most of the hydrogen on Earth exists in molecular forms such as water and organic compounds. For the most common isotope of hydrogen, symbol 1H, each atom has 1 proton, 1 electron, and no neutrons. In the early universe, the formation of protons, the nuclei of hydrogen, occurred during the first second after the Big Bang. The emergence of neutral hydrogen atoms throughout the universe occurred about 370,000 years later during the recombination epoch, when the plasma had cooled enough for electrons to remain bound to protons. Hydrogen is non-metallic except when it becomes metallic at extremely high pressures and readily forms a single covalent bond with most non-metallic elements, forming compounds such as water and nearly all organic compounds. Hydrogen plays a particularly important role in acid-base reactions because these reactions usually involve the exchange of protons between soluble molecules. In ionic compounds, hydrogen can take the form of negative charge, that is, an ion, where it is known as a hydride, or a positively charged cation species denoted by the symbol H+. The H+ cation is simply a proton, symbol P, but its behavior in aqueous solutions and in ionic compounds involves screening of its electric charge by nearby polar molecules or anions. Because hydrogen is the only neutral atom for which the Schrödinger equation can be solved analytically, the study of its energetics and chemical bonding has played a key role in development of quantum mechanics. Hydrogen gas was first artificially produced in early 16th century by the reaction of acids on metals. In 1766 to 1781, Henry Cavendish was the first to recognize that hydrogen gas was a discrete substance and it produces water when burned, the property for which it was later named. In Greek, hydrogen means water former. Industrial production is mainly from steam reforming of natural gas, oil reforming, or coal gasification. A small percentage is also produced using more energy-intensive methods such as the electrolysis of water. Most hydrogen is used near the site of its production, the two largest sites being fossil fuel processing like hydrocracking and ammonia production. Hydrogen can be deployed as an energy source in fuel cells to produce electricity or via combustion to generate heat. When hydrogen is consumed in fuel cells, the only emission at the point of use is water vapor. Combustion of hydrogen can lead to thermal formation of nitrogen oxides. Hydrogen atoms may embrittle metals. Molecular hydrogen is highly flammable, having the enthalpy of combustion to be negative 286 kJ per mole. Hydrogen gas form explosive mixtures with air in concentrations from 4 to 74%, with chlorine at 5 to 95%. The hydrogen autoignition temperature, the temperature of spontaneous ignition in air, is 500 degrees Celsius or 932 degrees Fahrenheit. Pure hydrogen-oxygen flames emit ultraviolet light and with high oxygen mix are nearly invisible to the naked eye, as illustrated by the faint plume of the Space Shuttle main engine, compared to the highly visible plume of a Space Shuttle solid rocket booster, which uses an ammonium perchlorate composite. The detection of a burning hydrogen leak may require a flame detector. Such leaks can be very dangerous. Hydrogen flames in other conditions are blue, resembling blue natural gas flames. The destruction of Hindenburg airship was a notorious example of hydrogen combustion, and the cause is still debated. The visible flames in the photographs were the result of carbon compounds in the airship's skin burning. Molecular hydrogen is unreactive compared to diatomic elements such as halogens or oxygen. The thermodynamic basis of how this low reactivity is very strong H bonds with a bond dissociation energy of 435.7 kilojoule per mole. The kinetic basis of the low reactivity is the non-polar nature of the hydrogen molecule and its weak polarizability. It spontaneously reacts with chlorine and fluorine to form hydrogen chloride and hydrogen fluoride respectively. The reactivity of molecular hydrogen is strongly affected by the presence of metal catalysts. Thus, while mixtures of hydrogen molecule and oxygen molecule or air combust readily when heated to at least 500 degrees Celsius by a spark or flame, they do not react at room temperature in the absence of a catalyst. The ground state energy level of the electron in a hydrogen atom is negative 13.6 electron volts, which is equivalent to an ultraviolet photon of roughly 91 nanometers wavelength. The energy levels of hydrogen can be calculated fairly accurately using the Bohr model of the atom, which conceptualizes the electron as a quad orbiting the proton in analogy to the Earth's orbit of the Sun. However, the atomic electron and proton are held together by electromagnetic force, while planets and celestial objects are held by gravity. Because of discretization of angular momentum postulated in early quantum mechanics by Bohr, the electron in the Bohr model can only occupy certain allowed distances from the proton, and therefore only certain allowed energies. A more accurate description of the hydrogen atom comes from a purely quantum mechanical treatment that uses the Schrödinger equation, Dirac equation, or Feynman path integral formulation to calculate the probability density of the electron around the proton. The most complicated treatments allow for the small effects of special relativity and vacuum polarization. In the quantum mechanical treatment, the electron in a ground state hydrogen atom has no angular momentum at all, illustrating how the planetary orbit differs from electron motion. Molecular hydrogen exists as two spin isomers, that is, compounds that differ only in the spin states of their nuclei. In the orthohydrogen form, the spins of the two nuclei are parallel, forming a spin triplet state, having a total molecular spin S is equivalent to 1. In the parahydrogen form, the spins are antiparallel and form a spin singlet state, having spin S is equivalent to 0. The equilibrium ratio of ortho to parahydrogen depends on temperature. At room temperature or warmer, equilibrium hydrogen gas contains about 25% of the para form and 75% of the ortho form. The ortho form is an excited state, having higher energy than the para form by 1.455 kilojoules per mole, and it confers the para form over the course of several minutes when cooled to low temperature. The thermal properties of the forms differ because they differ in their allowed rotational quantum states, resulting in different thermal properties such as the heat capacity. The ortho to para ratio in hydrogen molecule is an important consideration in the liquefaction and storage of liquid hydrogen. The conversion from ortho to para is exothermic and produces enough heat to evaporate most of the liquid, if not converted fast to parahydrogen. During the cooling process, catalysts for the ortho-para interconversion such as the ferric oxide and activated carbon compounds are used during hydrogen cooling to avoid this loss of liquid. Hydrogen gas is colorless and transparent. The phase diagram of hydrogen shows the temperature and pressure scales to be logarithmic. So 1 unit corresponds to 10 times change. The left edge corresponds to 10 raised to 5 pascals, which is about atmospheric pressure. Molecular hydrogen is not very reactive under standard conditions. It does not form compounds with most elements. Hydrogen can form compounds with elements that are more electronegative, such as halogens, fluorine, chlorine, bromine, iodine, or oxygen. In these compounds, hydrogen takes on a partial positive charge. When bonded to a more electronegative element, particularly fluorine, oxygen, or nitrogen, hydrogen can participate in a form of medium-strength non-covalent bonding with another electronegative element with a lone pair, a phenomenon called hydrogen bonding that is critical to the stability of many biological molecules. Hydrogen also forms compounds with less electronegative elements such as metals and metalloids, where it takes on a partial negative charge. These compounds are often known as hydrides. Hydrogen forms a vast array of compounds with carbon called hydrocarbons, and an even faster array with heteroatoms that, because of their general association with living things, are called organic compounds. The study of their properties is known as organic chemistry, and their study in the context of living organisms is known as biochemistry. By definitions, and I quote, organic compounds are only required to contain carbon. However, most of them also contain hydrogen, and because it is the carbon-hydrogen bond that gives this class of compounds most of its particular chemical characteristics, carbon-hydrogen bonds are required in some definitions of the word, and I quote, organic in chemistry. Millions of hydrocarbons are known, and they are usually formed by complicated pathways that seldom involve elemental hydrogen. Hydrogen is highly soluble in many rare earth and transition metals, and is soluble in both non-crystalline and amorphous metals. Hydrogen solubility in metals is influenced by local distortions or impurities in the crystal lattice. These properties may be useful when hydrogen is purified by passage through hot palladium disks, but the gas high solubility is a metallurgical problem contributing to the embrittlement of many metals. Compounds of hydrogen are often called hydrides, a term that is used fairly loosely. The term hydride suggests that the H atom has acquired a negative or anionic character, denoted H-, and is used when hydrogen forms a compound with more electropositive element. The existence of the hydride ion, suggested by Gilbert and Lewis in 1916 for group 1 and group 2 salt-like hydrides, was demonstrated by Mora in 1920 by electrolysis of molten lithium hydride, producing a stoichiometric quantity of hydrogen at the anode. For hydrides other than group 1 and 2 metals, the term is quite misleading, considering the low electronegativity of hydrogen. An exception in group 2 hydrides is beryllium hydride, which is polymeric. In lithium aluminum hydride, the anion carries hydride centers firmly attached to the aluminum ion. Although hydrides can be formed with almost all main group elements, the number and combination of possible compounds varies widely. For example, more than 100 binary boron hydrides are known, but only one binary aluminum hydride. Binary indium hydride has not yet been identified, although larger complexes exist. In inorganic chemistry, hydrides can also serve as bridging ligands that link two metal centers in a coordination complex. This function is particularly common in group 13 elements, especially in boranes and aluminum complexes, as well as in clustered carboranes. Oxidation of hydrogen removes its electron and gives H+, which contains no electrons, and a nucleus, which is usually composed of one proton. This is why H+ is often called a proton. This species is central to discussion of acids. Under the Bronsted-Lowry acid-base theory, acids are proton donors, while bases are proton acceptors. A bare proton H plus cannot exist in solution or in ionic crystals because of its unstoppable attraction to other atoms or molecules with electrons. Except at high temperatures associated with plasmas, such protons cannot be removed from the electron clouds of atoms and molecules and will remain attached to them. However, the term proton is sometimes used loosely and metaphorically to refer to a positively charged or cationic hydrogen attached to other species in this fashion, and as such is denoted H+, without any implication that any single protons exist freely as a species. To avoid the implication of the naked solvated proton in solution, acid aqua solutions are sometimes considered to contain a less unlikely fictitious species, termed the hydronium ion. However, even in this case, such sulfated hydrogen cations are more realistically conceived as being organized into clusters that form species closer to H9O4+. Other oxonium ions are found when water is in acidic solution with other solvents into clusters that form species closer to oxonium ion. Other oxonium ions are found when water is in acidic solution with other solvents. Although exotic on Earth, one of the most common ions in the universe is H3 plus ion, known as protonated molecular hydrogen or the trihydrogen cation. Binary indium hydride has not yet been identified, although larger complexes exist. Hydrogen has three naturally occurring isotopes, denoted hydrogen 1, hydrogen 2, and hydrogen 3. Other highly unstable nuclei, hydrogen 4 and hydrogen 7, have been synthesized in the laboratory but not observed in nature. Hydrogen 1 is the most common hydrogen isotope with an abundance of more than 99.98%. Because the nucleus of this isotope consists of only a single proton, it is given the descriptive but rarely used formal name protium. It is unique among all stable isotopes in having no neutrons. Hydrogen 2, the other stable hydrogen isotope, is known as deuterium and contains one proton and one neutron in the nucleus. Nearly all deuterium in the universe is thought to have been produced at the time of the Big Bang and has endured since that time. Deuterium is not radioactive and does not represent a significant toxicity hazard. Water enriched in molecules that include deuterium instead of normal hydrogen is called heavy water. Deuterium and its compounds are used as non-radioactive label in chemical experiments and in solvents for hydrogen 1 nuclear magnetic spectroscopy. Heavy water is used as neutron moderator and coolant for nuclear reactors. Deuterium also is a potent fuel for commercial nuclear fusion. Hydrogen 3 is known as tritium and contains one proton and two neutrons in its nucleus. It is radioactive, decaying into helium-3 through beta decay with a half-life of 12.32 years. It is radioactive enough to be used in luminous paint to enhance the visibility of data displays, such as for painting the hands and dial markers of watches. The watch class prevents the small amount of radiation involved from escaping the case. Small amounts of tritium are produced naturally by the interaction of cosmic rays with atmospheric gases. Tritium has also been released during nuclear weapons tests. It is used in nuclear fusion reactions as tracer in isotope geochemistry and in specialized self-powered lighting devices. Tritium has also been used in chemical and biological labeling experiments as a radiolabel. Unique among elements, distinct names are assigned to its isotopes in common use today. During the early study of radioactivity, various heavy nuclear isotopes were given their own names, but such names are no longer used, except for deuterium and tritium. The symbols D and T instead of hydrogen 2 and hydrogen 3 are sometimes used for deuterium and tritium, but the symbol P is already in use for phosphorus and thus is not available for prosium. In its nomenclatural guidelines, the International Union of Pure and Applied Chemistry (IUPAC) allows any of D, T, hydrogen 2 and hydrogen 3 to be used, although hydrogen 2 and hydrogen 3 are preferred. The exotic atom muonium, composed of an antimuon and an electron, can also be considered a light radioisotope of hydrogen. Because muon decay with lifetime 2.2 microseconds, muonium is too unstable to exhibit observable chemistry. Nevertheless, muonium compounds are important test cases for quantum simulation due to the mass difference between antimuon and proton. The International Union of Pure and Applied Chemistry nomenclature incorporates such hypothetical compounds as muonium chloride and sodium muonide, analogous to hydrogen chloride and hydrogen hydride respectively. In 1671, the Irish scientist Robert Boyle discovered and described the reaction between ion fillings and dilute acids, which results in the production of hydrogen gas. And I quote, having provided a saline spirit, hydrochloric acid, which by an uncommon way of preparation was made exceeding sharp and piercing, we put into a vial capable of containing 3 or 4 ounces of water, a convenient quantity of fillings of steel, which were not such as commonly sold in shops to chemists and apothecaries, those being usually not free enough from rust, but such as I had a while before caused to be purposely filled off from a piece of good steel. This metalline powder being moistened in the vial with a little of monasterium was afterwards drenched with more, whereupon the mixture grew very hot and belched up copious and stinking fumes, which together they consisted altogether of the volatile sulfur of Mars, or of metalline steams participating of a sulfurous nature, and joined with saline exhalation of menstruum, is not necessarily to be here discussed, but whensoever this stinking smoke proceeded, so inflammable it was, that upon the approach of a lighted candle to it, it will readily enough take fire and burn with a bluish and somewhat greenish flame at the mouth of the vial for a good while together, and that though with little light, yet with more strength than one will easily suspect. These are tracts written by the Honorable Robert Boyle containing new experiments touching the relation between flame and air. The word sulfurous may be somewhat confusing, especially since Boyle did a similar experiment with iron and sulfuric acid. However, in all likelihood, sulfurous should here be understood to mean combustible. In 1766, Henry Cavendish was the first to recognize hydrogen gas as a discrete substance by naming the gas from a metal acid reaction in flammable air. He speculated that this inflammable air was in fact identical to the hypothetical substance called phlogiston, and further finding in 1781 that the gas produces water when burned. He is usually given credit for the discovery of hydrogen as an element. In 1783, Antoine Lavoisier identified the element that came to be known as hydrogen, when he and Laplace reproduced Cavendish's finding that water is produced when hydrogen is burned. Lavoisier produced hydrogen for his experiments on mass conservation by reacting a flux of steam with metallic iron through an incandescent iron tube heated in a fire. Anaerobic oxidation of iron by the protons of water at high temperature can be schematically represented by the set of reactions. Many metals such as zirconium undergo a similar reaction with water, leading to the production of hydrogen. Francois Isaac de Rivaz built the first de Rivaz engine, an internal combustion engine powered by a mixture of hydrogen and oxygen. In 1806, Edward Daniel Clark invented the hydrogen gas blowpipe in 1819. The Dobrein's lamp and limelight were invented in 1823. Hydrogen was liquefied for the first time by James Dewar in 1898 using regenerative cooling and his invention, the vacuum flask. He produced solid hydrogen the next year. The first hydrogen-filled balloon was invented by Jacques Charles in 1783. Hydrogen provided the lift for the first reliable form of air travel, following the 1852 invention of the first hydrogen-lifted airship by Henry Clifford. German Count Ferdinand von Zeppelin promoted the idea of rigid airships lifted by hydrogen that later were called Zeppelins, the first of which had its maiden flight in 1900. Regularly scheduled flights started in 1910, and by the outbreak of World War I in August 1914, they had carried 35,000 passengers without a serious incident. Hydrogen-filled airships were used as observation platforms and bombers during the war. The first non-stop transatlantic crossing was made by the British airship R-34 in 1919. Regular passenger service resumed in 1920s, and the discovery of helium reserves in the United States promised increased safety, but the US government refused to sell the gas for its purpose. Therefore, hydrogen gas was used in the Hindenburg airship, which was destroyed in a mid-air fire over New Jersey on 6 May 1937. The incident was broadcast live on radio and filmed. Ignition of leaking hydrogen is widely assumed to be the cause, but later investigations pointed to the ignition of the aluminized fabric coating by static electricity. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.
Yeah.